Yes, sir.
Okay. Yeah. So I call your attention to assignment 3 that I posted as a file on the course webpage. It will not be graded, but treat it as an assignment. It's an important assignment. It covers sort of material at the beginning of the chapter on diagonalization, which you should really know. So I expect that you will work through it. And if you have any doubts, we can arrange a tutorial this weekend, and you can write to me also. Very good. So now we are dealing with inner product spaces. This is finite dimensional real inner product spaces. Was there a question? No. Okay. So a real inner product space is a real vector space with an additional structure on it, namely an inner product on the vector space. Okay, I have defined for you what an inner product is. So example, V is Rn, and the inner product is given vectors V and W, where V is an n-tuple of real numbers, and W is also an n-tuple of real numbers. Sigma I, Vi, Wi. This is not the most general inner product on Rn. So if A equal to Aij is a symmetric n cross n matrix, you can define something that depends on A, which is sigma I j Vi Aij Wj, and you can check this is bilinear and symmetric, but may not be positive definite. But there are matrices for which this is positive definite. If this is positive definite, the matrix A is said to be positive. So whenever I have a positive matrix and you get a corresponding inner product. Exercise. Let T, let me call it B, be any invertible matrix and define A to be B transpose. Let me call it B transpose B, any invertible n cross n matrix, B transpose B, prove that A is symmetric and positive definite and positive. So you see there are lots of inner products even on Rn. So with that out of the way, let us see. So
Sir,
we
could
have,
you show the question once again, the exercise? Yeah. Okay, sir.
So we have seen or talked about suppose V is a real inner product space. We define the norm of V to be square root, positive square root. We saw dVW equals V minus W is a distance. And this follows from the Cauchy-Schwarz inequality. Which says if you take any two vectors B and W, take the scalar, this is called the scalar product, and take the absolute value, it's less than the product of the norms. And I briefly, very quickly indicated the proof in the last lecture. It's there in the notes. Okay, so now we come to the very important notion. So given finite dimensional vector space, we have defined the notion of a basis. When a finite dimensional vector space has an inner product, when it's an inner product vector space, then there are special bases called orthonormal bases. So here is the definition. Let V be an n-dimensional real inner product space where basis V1, Vn is said to be, let me try and use the same notation as in the notes. Okay, I use U1 to UN in the notes, so let me just use that. Is said to be an orthonormal basis if Ui Uj is delta Ij. So this is our friend, the Kronecker delta. So explicitly, this means each basis vector has unit length. So in other words, norm of U, which is Ui in a norm of Ui, which is norm of Ui inner product Ui square root of half, is 1, and this is equivalent to saying Ui is 1 plus Ui Uj inner product is 0 if I is not equal to j. So orthonormal bases exist. So let us see the example of V equal to R2 with the standard inner product. So if U1 is 1, 0, and U2 is 0, 1, this is an orthonormal basis. Right? Because you can check U1 in a product U1 is 1, U2 in a product U2 is 1, and U1 in a product U2 is 0. But this is not the only orthonormal basis. Here is another one. U1 prime equals 1 over square root 2, 1, 1, 1. And U2 prime is equal to 1 over square root 2, 1 minus 1 is another orthonormal basis. Why? Because U1 prime, comma U1 prime is sum over I, U1 prime 1, U1, U1 prime 1 plus U1 prime 2, U1 prime 2, which is sum over, well, I shouldn't have sum over, because this is equal to 1 over square root of 2 into 1 over square root of 2 plus 1 over square root of 2 into 1 over square root of 2, which is 1. Similarly, U2 prime inner product is 1 plus, but U1 prime, U2 prime inner product is 0. So in pictures, these are, so this is the first basis, U1, U2, and this is the second basis. Actually, maybe not. Okay, so there are, even in the case of R2 with the standard inner product, there are lots of orthonormal bases. So we will now prove if V is n-dimensional in a product space, it has an orthonormal basis. In fact, we will give an algorithm for starting with any basis and producing an orthonormal basis. We will describe an algorithm whose input is any basis V1, V2, Vn, any basis, not necessarily orthonormal, and output U1, U2, So this is called the Gram-Schmidt orthogonalization process. Gram-Schmidt orthogonalization process. Okay, so this is how it goes. Okay, so let us apply it to a case of R2. Okay. So I take R2 with the standard inner product, and I start with the following basis. So the first vector is 2, 0. So this is V1. And the second vector is V2, which is 1, 1. Okay. So is this an orthonormal basis for the standard inner product?
No, sir.
No. Yeah. Why is it not orthonormal?
So it is the inner product is not 0 and the norm is also not 1.
Okay. So V1 and V2 are not, their inner product of V1 and V2 is not 0. And also the length of V1 is, what is the length of V1?
2.
It is 2.
And the length of V2?
Square root 2.
Yeah. Is this all clear to everyone? Does everybody agree with this? Amit, Parikh?
Yes, sir.
Okay. Ayan, Nath, do you agree with this? That this is not orthonormal. The lengths are not the 1 and they are not, the inner product is not 0.
Yes,
Gautam?
yes, sir.
Why?
Yes, sir. Yeah.
Yeah, yeah. Okay, so what you do is because this is an ordered basis, so by the way, the Gram-Schmidt process works with ordered basis. Okay, so at some point we have started talking about ordered basis without my explicitly telling you this. Okay, so the basis vectors come in an order. So I take the first one, which is V1, and I cure its basic problem with V1 is that its length is not 1. Okay, so what is the least amount of work I can do to make its length 1?
So scale it appropriately.
Yeah. So you just define U1 to be definition V1 divided by its length. Now, why is the length non-zero? Why can I do this division?
Because your vector.
Sorry?
So it's element of
No.
basis, so it has
It's
to be
V1
Norms
is an
are
element of a
positive normal.
basis, so it cannot be 0. And if I have a non-zero vector, its length cannot be 0 according to the axioms of an inner product. Okay, so so what I have done so far is legitimate. So I've got myself U1. Okay. Now, unfortunately, V2, there are two problems with V2. V2 is not of length 1, and V2 is not, the scalar product of V2 and U1 is not 0. Okay. So I have to take care of that. So what do? You just write V2 as something that's parallel to U1. So V2 minus, sorry. You just write V2 in this form, and then I claim A V2 minus V2 U1 u1 is non-zero, b v2 minus v2 u1 inner product u1 is 0. So from V2, I manufactured this other vector, which has these two properties. That first of all, it's a non-zero vector, and its inner product with U1 is 0. Okay, so let me draw this U. So this is U1. This is see, the length of V1 was 2 in this case. So when I divide V1 by its length, I get basically the vector 1, 0. So what I have done is I have written V2 as a sum of a vector in the direction along U1 and in the direction perpendicular to it. So let me I don't want to draw that because I'm. So first of all, let us prove A and B. Okay, B is easy. This is 1. Okay, so we approved this. Now, why is A true?
Because
So
they are
because
linearly
it's
independent.
so
Yeah,
because
there are many answers.
it won't form a basis then.
Yeah, suppose V2 minus V2 U1 is 0. Then V2 equals V2 U1, which is V2 over V1 squared. So this means that V2 is a multiple of V1. So, but V2 and V1 cannot then be a basis for cannot be a part of a basis. Contradiction. Since V1 and V2 are part of a basis and cannot be linearly dependent. Very good. So, so now what I will do is we will define U2 prime to be equal to V2 minus V2 U1 and then set U2 to be U2 prime divided by its norm. Now we have u1 equal to 1, u2 equal to 1, and u1 equal to 0. So this we did in the case of R2, but exactly the same procedure. You have to do an appropriate induction. Will give you this algorithm whose input will be any basis, and whose output will be an orthonormal basis that you get in a systematic and deterministic way from the original basis. Okay, I will not repeat the general construction. It is given in the notes. So now we come to a very, very important construction that's available to you only when you have inner product space. Okay. So that is the notion of an orthonormal complement. Okay. Let V be an n-dimensional vector space. And W in V be m-dimensional. And to have a non-empty discussion, meaning to have to rule out uninteresting things, we will assume that m is not equal to n and is not equal to 0. So, in other words, W is not equal to V and is not just consisting of the 0 vector. Okay. A supplement. So remember, at the moment, V is just an n-dimensional vector space. It could even be complex, and we are not talking about inner product yet. Okay. So, but I'm going to define the notion of a supplement, which doesn't require an inner product. And note, it is a supplement. So, and not the. So, so this is this tricky English thing. Whenever you say I'm signaling that there could be many choices. And when I say the in a definition or in a statement, I'm signaling that there is only one. Okay. So when I say a supplement, you should really note, I mean to tell you, and I'm signaling to you that this is not unique. A supplement to W in V is n minus m dimensional subspace W prime such that V equal to W direct sum W prime, i.e. Every vector V in V can be written uniquely as a sum V equal to W plus W prime, where this belongs to W, this belongs to W prime. So supplements exist. That's not difficult, but they are not unique. Supplements exist. So those who wonder, you can give a proof. So I will not why, but
Sir.
not one second. Yeah.
So I was just saying that the reason why there's multiple is because we can take any basis of W and then extend it to a basis of V, and then the basis vectors which of V from this basis which are not in W will form W dash essentially, and then I can
Yeah.
write. So since there's like lots of choices for any basis of W, then that's why we have
Very
lots of
good,
choices.
very good, very good, very good. Yeah. But you know that so since but there is a, so how do I parameterize supplements? So here is an example. So take V to be R2 and W to be the x-axis. Okay, so I should be careful. So I should not draw the XY plane. I should just draw, here is 0, 0. Well, here is the 0 of the plane. So yeah, so let me not call V R2. V is the, yeah, so let me, because when I say V is equal to R2, already various other things come into play. V is a two-dimensional real vector space, and W is a one-dimensional subspace. So, so let's assume that V is the plane of my iPad. Here is my origin, and W is yeah, this is W. Now, give me some choice of W prime.
Any line through origin but not equal to W.
Yeah, yeah. So any line through the origin but not equal to W. Okay, so supposing W prime is another one. No, let me not talk about parameters. So does everybody agree with this, that any line through the origin but not equal to W prime, not equal to W gives me a supplement, in the sense that this plane of this iPad is the direct sum of W and W prime. Any vector on the plane can be written. So take any vector V. I can write it uniquely as a combination of W and W prime. Okay, but now suppose we, yeah, so this is the notion of, so by the way, I will come back to this question of how to parameterize the choice of supplements. I don't want to go too far from the inner product situation, but now suppose V is an inner product space. Suppose now that V has an inner product. So since we have only defined the notion of an inner product for real vector spaces, we will assume that V is a real vector space. Okay. Then define W prime to be W in V, such that W inner product, so W prime in V says that inner product with every W, every vector in the capital, in the subspace W is 0. I claim W prime is a supplement. Okay. So then I have chosen, if this is, so for the moment you believe me, but then first of all, let me now, I've been going fairly fast. So let me now stop and ask, give you time to ask questions. Any questions?
Yes, sir. I had a question.
Yeah.
When you're doing the orthogonalization process,
Yeah.
I didn't get why the resultant vectors should be a
Mhm.
basis. I didn't fully get why they need to be a basis.
Yeah, so it's not your fault. I went in a hurry. So I suggest you read the notes and you work it out. It is not difficult.
Okay, sir. I'll do that.
Yeah,
Thank
yeah,
you.
yeah.
Sir, I have a question regarding exercise question in the notes. So can I ask it here or should I mail you?
Exercise posted in the notes, is it?
Yes, sir.
Why don't you write to me?
Okay,
I
sir.
mean, see, I don't want to break the flow of
Oh,
this
yeah, okay.
lecture.
Okay.
So if there are questions regarding inner product spaces or what we did today, I think that's this is a good place to address them. Srimati, are you there?
Yes, sir. Yeah.
So are you
Yes.
hanging on?
Yeah.
Yeah.
Uh,
Because, I
so,
mean,
but I didn't.
yeah, sorry, go ahead.
No, in the first page, I didn't understand the notations. When you talked about a symmetric n cross n matrix and you defined the inner product. So here. No. The previous page.
Yeah.
Previous page. Yeah. No, I didn't understand the sum. How is it a definition or?
Yeah.
Is that-
So I define something that depends on A. So hence a subscript here. So this is the definition. Yeah, thank you. Then you can check that this is bilinear in V and W. That's very easy. If V is a sum of two vectors V and V prime, the right-hand side will be sum of the corresponding terms. It's symmetric in V and W. That follows from the symmetry of A. Okay, remember, A has to be symmetric. But then what is not guaranteed is that this is a positive definite. So this thing that I have defined with a subscript A satisfies properties 1 and 2 of an inner product, but for 3, you need the metrics to have certain properties. And then the exercise says, if you take any invertible n by n matrix and define A to be B transpose B, then this is will be symmetric and positive definite. So
Yes, sir. No, I'll work through it. I just had a
yeah. No, since I use the opportunity just to repeat this. Any other questions?
No, sir.
I have a question. Are all positive matrices of this form, of the form B transpose B?
Yeah. It's proved in the notes. But note that A does not uniquely determine B.
Okay, thank you, sir.
Yeah. Any other question? Yeah. Yeah. Okay. So So now the claim is that if there is a real inner product space and a subspace W, then that among all the supplements to that subspace, there is a God-given one that uses the inner product. The supplement consists of all vectors whose inner product with vectors lying in W is 0. So, for example, if going back to the picture above, if now, so instead of working with the plane of my iPad, if it's R2 and and W is the x-axis, then W prime, according to this definition, will be
So y-axis.
to claim it, but question, if V is R2 with the standard inner product, with standard inner product, and W is the x-axis, what is W prime? So this is V. V is R2, so I am allowed to draw the axis, and the x-axis is W. What is W prime? Look at the definition of W prime and tell me.
Y-axis.
Yeah. The W prime consists of vectors which are perpendicular to any point on the x-axis. That's precisely the y-axis. So this is W prime. If W is this, what is W prime? It will be this. Another question. If V is R3, and again, W is the x-axis. So let me.
Excuse me, sir.
Just 1 second. Yeah, there was a question. Tell me.
No, sir. I got it cleared. I mean.
Yeah. Okay. Okay. So now I'm asking again. So now take V to be R3 with the standard inner product, and take W to be the x-axis. What is W prime?
YZ plane.
YZ plane.
It's a YZ plane. So it is all these guys. Very good. So okay, so now proof of the claim. Okay, so we need a notation for this special choice of W prime, which uses the inner product, and the one standard notation is W with this sign, and it's often says W perp. Perp is short for perpendicular. The perpendicular to W. Okay, so this is the notation. So here is a proof of the claim. Okay. One, there are two parts of this claim. D is W plus W per to W intersection W per is 0. So every vector in B can be written as a sum of a vector in W and a vector in W per, and the intersection of W and W per is 0. So first proof of 2. Suppose W is in W in intersection W per. We have W inner product W is 0 because W is in W and W is also in W per. So the inner product is 0 by the definition of W per. This implies the length of W is 0, or well, by the axioms of the inner product, by axiom of inner product. So we prove 2. Now, proof of 1. Proof of 1. Choose orthonormal basis U1, UM of W. So W is an inner subspace of V of dimension M. V has an inner product. So W inherits that inner product, because if I can define the inner product of any two vectors in V, I can certainly use that to define the inner product of any two vectors in the subspace W. Okay, so and I can by the orthonormalization process, or in any case, there is an orthonormal basis of W. So choose one. Define a map P from V to V by P acting on B is sum over I equal to 1 to M B inner product UI. So this is a linear map from V to W. So we have V equal to V minus sigma V UI plus sigma I equal to 1 to N V UI. This belongs to W per, sorry, this belongs to W. And the claim is that this belongs to W per. Shall I leave this as an exercise, or shall I? Actually, this is a good time to take a break, and you guys try and figure this out for a few minutes, and then I'll come back and do this. This is quite easy. But before I leave you to figure this up, let me make sure that everybody knows what we are up to. Hello, can you hear me? There seems to be some
Yes, sir.
bandwidth problem. Hello, can you hear me?
Yes, sir.
Yes, sir, we can hear.
Yeah. So I've been going a bit fast, so I'm going to leave you to figure this out. But before I leave you, if you don't know what you are supposed to figure out, that's somewhat unfortunate. So I'm waiting here. So anybody who's puzzled as to what's going on, please stop. So I'll explain and then go away. So let me repeat. What we are doing is, okay, we start with a finite dimensional vector space, real or complex, it doesn't matter. Then we remark that given a subspace, it has supplements, but not unique. Then I claim that if I have a finite dimensional vector space with an inner product, then among all supplements, there is a natural one which uses the inner product called the perpendicular of that subspace. As the name implies, it consists of vectors whose inner product with every vector in the subspace is 0. I illustrated this in the case of R2 and 2 subspaces. But now I'm proving that in general, the claim is true, that the perpendicular of a subspace is a supplement. What does that mean? That means that the vector space, given any inner product space and a subspace, that vector space is the direct sum of the subspace and its perpendicular. What does it mean to say a vector space is a direct sum of 2 subspaces? Well, if that vector space must be generated by these 2 subspaces and their intersection must be 0. Because if that is the case, any vector in the vector space can be written uniquely as a sum of a vector in sum of 2 vectors, one lying in the first subspace and the other lying in the second subspace. So we have taken V, we have taken W, and we have taken W per, and to prove that V is the direct sum of V and W, we prove the 2 parts separately. We prove that the intersection of W and W per is 0, that is this part. And then we prove that any vector in V can be written as a sum of a vector in W and a vector in W per. Part 2 I proved here. Now I'm proving part 1. I'm taking a vector in V, writing is adding and subtracting this term, and then the claim this term is clearly in W because the ui's I running from 1 to m form a basis of W. So this is in W is clear. So what you have to check is that what is left is in W per. Okay. In other words, you have to prove that this, its inner product with every vector in W is 0. But note that every vector in W is a linear combination of the ui's. So it's enough to show that this inner product with every ui is 0. Okay, that's a hint. With that hint, I'm going to take a break, have my cup of tea. Okay, I'm back. Can you hear me? Hello.
Yes, sir.
Yeah. So did you guys try? So I want to hear from anybody who's kind of tried and got stuck.
Sir, I tried. I'm not getting it. I mean,
Okay. So
maybe I will need to try more, but
no,
from
yeah,
what I
sure,
have tried, sir.
yeah. So we do the following thing. So question. Yeah. So this is the kind of thing. So in fact, I had given you the hint. First, let uj be one of the basis vectors u1 to um. Remember, this is an orthonormal basis of one of the orthonormal basis vectors of W. Okay. Then take V minus sigma I equal to 1 to M V ui uj. So I'm taking any vector V, taking this combination and taking the inner product of that resulting vector with one of the basis vectors of belonging to this orthonormal basis. Now, by the bilinearity of the inner product, this is equal to V uj minus sum over I equal to 1 to M d ui. Remember, these are scalars. These are scalars, so I can pull them out. That's what I have done here. Do you follow this step?
Yes, sir.
Hello?
I think I see what to do.
Does everybody follow this step? If anybody doesn't follow this step, please tell me. Bhaumik, Snehansu Bhaumik, do you follow this step?
Yes, sir.
Okay. Now, Rishikesh Srinivasan, what can you tell me about these terms? Hello, are you there? Saumil Bakshi, are you there? Swaminathan Rajagopal?
Yes, sir. Sir,
What
you would get V inner product of V and uj from the whole sum.
Why is that?
So because it's an orthonormal basis, and if
these
I
are
not,
0 unless I equal to j, in which case it's 1. So this sum, as you said, is just V uj. Okay, so you get V uj minus uvj, this is 0. So this vector V minus sigma I equal to 1 to M V ui, this vector has inner product 0 with every one of the basis vectors u1 to um of W. Now, any vector, in W is a sum of these. So this implies that's it. That is what was needed to be proved. Rishikesh Srinivasan, do you see this? Yeah, Okay, good. Okay, so okay, I think I should not go on now. I think I'll stop now. I will ask you to read the next two sections before the next lecture. In fact, the rest of this chapter before the next lecture, I will talk about it, but we are really tight on time, so it will really help if you come prepared. I'm going to go quite fast. So I'm going to stop now because I've covered a lot of material. I don't think it's realistic to cover more. I will